These days, no matter which reputable science journal you open, one headline stands out: the detection of the most energetic neutrino ever discovered. While the scientific community is abuzz with excitement, there is an unusual silence in popular science media. To exaggerate a bit, this discovery is almost as important as the discovery of the atom, yet on platforms like YouTube, the topic has not gained the expected traction. YouTube's algorithm seems to predict that this subject has a low chance of attracting views. But this time, it is wrong. On February 13th, the ARCA detector part of the KM-3 Neutrino telescope, located 3,500 meters deep in the Mediterranean Sea, observed the highest energy neutrino ever recorded. The energy of this neutral particle was calculated to be a staggering 220 peta-electronvolts. To put that into perspective, this is nearly 10 times greater than the most energetic neutrino previously detected by the IceCube telescope. The research paper states, while the energy of this ghost particle does not exceed theoretical limits, its observed frequency is much higher than what current models predict. This means that either our existing models need to be reconsidered, or we are on the verge of a new physics breakthrough. Yes, you heard that right. This neutrino, emerging from the depths of the Mediterranean, could be opening the door to a new law of physics. A total of 360 scientists from 68 institutions across 21 countries have contributed to this discovery. These numbers alone highlight the significance of this finding. According to 2010 estimates, the initial cost of the project was 250 million euros. The latest exact figure is unknown, but one thing is clear: science requires patience. Why is this discovery so critical? Let's break it down step by step. First, we need to understand what this particle is. A neutrino is a fundamental particle with no electric charge, an extremely small mass, and almost no interaction with matter. Because of these properties, it is often called a ghost particle. Neutrinos travel at nearly the speed of light and are among the most abundant particles in the universe. Trillions of them pass through our bodies every second, yet they rarely interact with matter. This makes their detection incredibly difficult, but when they are detected, they carry information so significant that it can shake the foundations of physics. In experiments conducted in the late 1920s, scientists noticed that the energy released during beta decay did not match expected values. This was a major challenge to the law of energy conservation at the time. The energy carried by the emitted electron appeared to be less than the initial total energy. The results seemed to suggest that some energy had disappeared, a situation that was completely unacceptable for physicists. In fact, they were on the verge of shutting down their research altogether. By 1932, Wolfgang Pauli, lost in the perplexing depths of physics, proposed a solution to this inconsistency: an unknown, electrically neutral, and extremely light particle might be carrying away the missing energy. This particle was later named the neutrino. It is said that Pauli was so desperate that he famously remarked, "We will never be able to observe such a particle directly, but I am proposing it to save my calculations." The name for the particle Pauli theorized was given by Enrico Fermi, the Italian physicist known for his work on the Manhattan Project. Let's be honest, he designed the most critical aspect of the atomic bomb. If we derive the name for the large neutral particle from the Latin word for neutral, Fermi suggested, then why not call this nearly massless neutral particle a neutrino? Let's also take a moment to appreciate Fermi, who, despite leading such a challenging life, managed to remain cheerful. His contributions to physics, including the first controlled nuclear chain reaction, were groundbreaking. Fortunately, in 1956, Clyde Cowan and Frederick Raynes experimentally confirmed the existence of neutrinos by detecting those emitted from a nuclear reactor, validating Pauli's prediction and putting physicists' minds at ease. The law of energy conservation was safe once again. As research continued, different types of neutrinos were discovered, and it was determined that these particles, despite being incredibly light, do have mass. By 2015, Takaki Kajita and Arthur B. McDonald were awarded the Nobel Prize in Physics for their discovery of neutrino oscillations. A tiny particle had made its way to Nobel Prize recognition. Now, where do neutrinos fit into our daily lives? Imagine something that has energy and mass but almost never interacts with matter. Trillions of them pass through you every second. Why don't they interact? Because they have no electric charge and their mass is vanishingly small. Electromagnetic forces don't apply to them. While this lack of interaction is crucial for our health, what's even more exciting is that since neutrinos remain unaffected by their surroundings after they are emitted, they carry pristine information about their source. For example, we may never be able to directly observe the singularity of a black hole, but a neutrino that bounces off the event horizon could bring us crucial insights. This is why massive investments are being made in this field. These insights could be a treasure trove of knowledge. But how do we detect something with no electric charge and almost no mass? Interestingly, the very properties that make neutrinos difficult to detect can also be an advantage. Consider this. Among the countless cosmic rays traveling through space, there are also ghost particles, neutrinos. But unlike cosmic rays, which interact with matter, neutrinos do not. If you try to detect these particles in a city center, cosmic rays will still be present in large numbers, making it difficult to isolate neutrinos. However, 3,500 meters below the ocean surface, most cosmic rays are absorbed by the surrounding matter. What remains are the elusive ghost particles. This is why neutrino detectors are built deep underground beneath glaciers or at the bottom of the ocean. The deeper you go, the more likely it is that what you are detecting is truly a neutrino. As seen in the pattern, the deeper you go, the closer you get to a Nobel Prize. But how do we catch a neutrino thousands of meters below the Earth or the ocean? Let's be even more realistic. How do you detect something that barely interacts with matter? First, we need to understand that while neutrinos rarely interact with matter, they do so on occasion, and that is how they can be observed. Most of the time, they pass through everything unnoticed. However, sometimes a neutrino collides with an atomic nucleus or an electron. When this happens, charged particles are ejected at high speed, producing a phenomenon known as Cherenkov radiation. In simple terms, Cherenkov radiation is the flash of light created when a particle moves faster than the speed of light in a dense medium such as water or ice. This effect is similar to the sonic boom of a jet breaking the sound barrier. So, if you are 3,500 meters beneath the ocean and detect a flash of light in your sensors, chances are you've caught a neutrino. In underwater detectors like KM3net or ice-based detectors like IceCube, the detection process works as follows. The detectors are composed of modules positioned at specific depths. There is no single massive sensor covering the entire 3,500 meters. Instead, optical modules are arranged along vertical cables known as strings. These strings are anchored to the ocean floor, with optical sensors spaced at intervals. Each string holds dozens of sensors, and multiple strings together form a large detection network. These sensors detect the Cherenkov light emitted when a neutrino interacts with matter. But why do some neutrinos interact while others pass through without any interaction? First, neutrinos with higher energy have a greater probability of interacting. Second, it comes down to being in the right place at the right time. You might call it luck. A neutrino must pass through an atomic nucleus at precisely the right angle and moment to trigger an interaction. This requires perfect timing, and the probability of such an event is incredibly low. And lastly, the most important factor, the nature of quantum probabilities. To simplify, the likelihood of a neutrino interacting with matter is governed by quantum mechanics probability distributions. We can say, with 99.99% certainty, that a neutrino will pass through matter without any interaction. However, there is an extremely small probability that it will collide with a proton or neutron. The neutrinos that do interact are like the mischievous characters from a quantum version of Alice in Wonderland. Now, we know what a neutrino is, why it matters, and how it is detected. But what happened in February 2025? That was when the KM3 net neutrino detector, positioned 3,500 meters deep in the Mediterranean Sea, detected the highest energy neutrino ever recorded. This particle carried an astonishing 220 peta-electronvolts of energy, 30 times more powerful than previous records. Typically, we are used to detecting neutrinos that originate from the sun, and their energy levels tend to be fairly consistent. However, high-energy neutrinos like this one take us far beyond our galaxy, toward the vast unknown of the universe. Why is this neutrino's high energy so important? A colossal energy level of 220 PeV indicates that this neutrino did not originate from an ordinary event. It must have come from either a supermassive black hole or an extraordinary gamma ray burst, something beyond our technological reach. In other words, 3,500 meters beneath the Mediterranean, we have received a message from either a supermassive black hole or an unimaginably powerful cosmic explosion. This is exactly why scientists believe it originated from beyond the Milky Way. And here's the shocking part. The research paper explicitly states that this neutrino's energy exceeds what current models predict. That means we may need to reconsider our existing theories or be on the brink of discovering new physics. This is precisely what happened in February 2025. The KM3 net detector, submerged 3,500 meters deep in the Mediterranean, detected the most energetic neutrino ever recorded, 220 peta-electronvolts, nearly 30 times more powerful than previous records. Unlike the neutrinos we usually detect from the sun, which have relatively stable energy levels, such a high-energy neutrino points to a source far beyond the Milky Way. This energy level suggests it was produced by either a supermassive black hole or a cataclysmic gamma ray burst. In simple terms, a cosmic message has reached us from 3,500 meters beneath the Mediterranean, a signal from a black hole or a violent cosmic explosion. That's why scientists suspect this neutrino came from outside our galaxy. The research paper states it clearly, the energy of this neutrino is higher than what current theories predict. This means either our established physics models need revision, or we are on the verge of a groundbreaking discovery. But how can we determine that an almost undetectable particle traveled over 100 light-years to reach us? The answer is surprisingly simple. Imagine a ball traveling through space without hitting anything. In a frictionless environment, it continues in a straight line. The moment you spot it, you can trace its trajectory back to its origin. This is exactly how we identify a neutrino's source. According to the latest research, the study is still ongoing, but there is strong evidence suggesting that this neutrino may have originated from a black hole. If that turns out to be the case, what will this neutrino reveal to us? Neutrinos retain the properties they had at the moment of their creation because they do not interact with matter. This means they could provide us with unprecedented insights into the acceleration of particles near a black hole, the structure of its surrounding magnetic fields, and even its quantum state. A thrilling new era for physics is about to begin,